All right, welcome everybody. Let's get stuck into it. This is what month is this? This is June. I've lost all sense of space and time. So welcome to the June Sydney DevOps Meetup. I'm Lindsay, my co-organizer Michael is in here as well. We've run this for the last couple of years. It's lovely to have you all here and aboard tonight. First up, I would like to do oh my God. Sorry, my slides are. I've had a migraine all afternoon and I feel completely disconnected from my body. So you're just going to have to wait a moment while I slowly muddle through this. Here we go. I'm trying. Normally I have this up in another tab, but tonight I'm just going to peel back the curtains because I feel like shit and I don't care that you can see behind the curtains. I would like to acknowledge the traditional owners and custodians of country throughout Australia, which in my case is the Guringai people, and recognize the continuing connection to land, waters, and culture. We pay our respects to their elders past, present, and emerging. Sovereignty was never ceded and treaties never been signed. It always was and always will be Aboriginal land. So, as I said, welcome to the June meetup. Quick refresher for the code of conduct here. We don't tolerate harassment of meetup participants in any form. All communication should be appropriate for a professional audience. And please remember that harassment and sexist, racist, or exclusionary jokes are not appropriate at DevOps Sydney. The great thing about doing these meetups online is that it's really easy to boot people. So if you have a problem, let me know. I haven't had to do that until now, but there's always a first time for everything. So that's fun and exciting. All right, for tonight's agenda, we've got the intro, which is the thing that you are listening to right now. We're going to launch straight into the main talk very soon. We've got an events job section, and we're going to have one lightning talk at the end. Quick reminder for the job section. So the way that works is that if you're looking to fill a position, either you are on the hunt for a new role or you are looking to fill a role, it'll have 30 seconds to either pitch yourself or pitch the role. I'll let a few more people in. There we go. And that's going to happen after the main talk. So get your pitches ready. So the main talk tonight, we've got Avishai dialing in remotely. Well, we're all dialing in remotely, but Avishai is dialing in particularly remotely tonight. Well, for us tonight, for him, it's the morning, talking about the art of debugging. And then lightning talk, we've got Michael Richardson talking about scaling SBS on demand for season 4 of Handmaid's Tale. So both of these are going to be super interesting. I'm really excited to see them. Hopefully you can do all the little Zoom chat things. There we go. And we've got Jason coming in from chilly Melbourne. That's lovely to have you here, Jason. You're actually preempting what I'm going to ask in a second. Who here is joining the meetup for the first time? You can either use a little hand thing, or there's a few people popping stuff in the chat. That is lovely to see. We've got Alexis, who is coming in from Brizzy. We've got Alareza, Michael Delsman. Wow, it's a heap of first time as well. That is really lovely to have all of you here. We've got folks coming in from the South Coast. Well, you're actually all preempting my next question, which is, how far have you come? Avishai, you don't get to answer this yet because I think you might be the winner. We've got Benjamin Robertson coming in from Canberra. We've got Jesse from Melbourne. Fantastic. The Sydney label on Sydney DevOps doesn't really feel that apt anymore because of the 30 people that we have here. It's like half the people have popped up and said, I'm not from Sydney. So that is lovely to hear. Oh, we even got Rowan saying that he is from Sydney. So it's good to know that there are some people from Sydney still here. Oh, thank you. I just had my dinner delivered. That was very good timing. Is there anybody overseas who is joining us today? And Avishai, you can put your hand up for this one. We've got Avishai coming in from Israel. Anyone further afield than Israel? Specifically from Tel Aviv. Perfect. All right, I think Avishai might win that one tonight. Again, for us tonight, for him in the morning. So congratulations. Oh, we've got Vijay coming in from Frankfurt. Well, that's fantastic. Oh, you pipped at the post, Avishai. Well, welcome aboard. It's lovely to have some international guests here as well. All right, we're still in this holding pattern of online meetups continuing until the vaccine is available for everybody, given the current pace of vaccine rollout in Australia. We may just be doing these online meetups forever, but we'll see how that goes. I did actually have a tentative plan to maybe try and get back into an in-person meetup starting this month, but that hasn't happened. And look, the online meetups tend to be working pretty well for us. So we'll see how that goes. But just sort of setting that expectation there. And the nice thing about doing these online meetups is that we have a whole bunch of lovely international people joining us, and also just domestically as well, people coming from outside of Sydney, which is lovely. So let's just jump straight into it. We've got Avishai talking about the art of debugging. I'm going to stop my screen share and hand it over to him.
Okay, so thank you. Let me just see if I can share my screen real quick. And can you see my screen?
That's looking good.
Okay, awesome. So I'm going to be talking today about the art of debugging. And debugging is one of those things that people kind of assume it's an innate talent. You know, some people can debug and they do it marvelously, and they do an amazing job of debugging, and other people just can't debug.
Avishai, before you go on, I don't know if you're sharing the screen that you're meant to be, but we're currently seeing your work Slack and Spotify.
That is not what I'm supposed to be showing. So 1 second. So it should be a slide. So let's see. Can you see this?
Still your Slack.
Still my Slack.
Yeah.
That's not good.
Just put your presentation in Slack. It will be fine.
Ah, okay. That works perfectly.
Possibly in Spotify.
Yeah.
Now it's VS Code, and now.
Oh yeah, now you're going to see my horrible code. That was a big mistake. One should never do that. How do I new show or what?
Are you just wanting 30 people to troubleshoot your code?
Yeah, thanks for the help.
Yeah,
I don't think 30 people, even 30 people can't debug my code. It's you don't want to know how bad it is. Let's try again. Share screen, desktop. It's like advanced or something. That portion of screen. Basic. Now maybe?
No, same screen as before.
VS Code and Spotify.
How do you? What?
It was working perfectly just before when we were testing.
Yeah, maybe I just need to switch desktop or something. 1 sec. Let me try this. Don't use Wayland. That's all I can say about this.
This is a very meta talk because we're already debugging.
Yep, exactly. So let me see if I can. Let's try this again. I think it relates to what was on screen when we show. Optimize for movement. No, it's not it. And let's see if you can.
Same as before.
One
VS
sec.
Code and a little sharing screen, I'm guessing.
And now?
Nope, same thing as before.
Okay, this is very annoying. Okay, so let me see if I can do something else, because otherwise it's going to just take too long. Oh, shit. So I'm just gonna, let's do this. I'm just gonna give you my link, okay, to the slides, and
Oh yeah, I'm happy to share that. Yep, that works.
Yeah, it's just gonna work much quicker, and
Let's
yeah,
do
I
that.
apologize for it. Yeah, I'm just gonna give it a last attempt, and if that doesn't work, then we'll just continue without this.
No worries. The irony is that we did a test just before everybody joined, and it was working perfectly. So technology, not even once.
I do apologize for this.
All good.
And now?
It looks different. We've got a bunch of.
You don't see the slides?
No, we see a bunch of lines.
Oh wow, this is unbelievable.
It's like, yeah, it's like it's X and Wayland, something in there, I think. So yeah, just
Show me the slides and I'll share them up on the screen. Not
Yeah.
a problem at all.
So let's do this. I'm going to put the link in the slide in the chat.
Perfect. All right, I'll get them here and just yell out next slide and I'll pop it up.
Yeah, I'll do that. Where's the Zoom thingy? Oh wow, now I lost Zoom. Okay, 1 sec.
All good. Take your time.
We can maybe start with Michael and then do like reverse meetup if we need more time.
That's not a bad idea. If we can't get this going in the next 30 seconds, we'll switch to you, Michael.
Sure thing. I'm on a new Linux desktop, so I'm.
Wow, is it the year of Linux on the desktop?
2021. That's it.
Love it. Hey, and it is nothing on the screen there. It's just stripy lines.
Okay, so I'm just going to give you the link and that's it. We're not going to do this way.
Is it Google Slides or something like that?
Yep, Google Slides. So
Perfect.
actually, you can just follow up on the when I switch slides.
Yep.
So you can do whatever.
Just let me know when you sent that.
So,
If you're doing it in the chat or elsewhere.
chat. Just put it in the chat. There you go.
Perfect. And everybody can follow along at home as well if they want. All right, let me share my screen. Let's get this going.
Okay. Yeah, sorry about that. Okay, so debugging. So debugging is one of those things that are considered an innate skill, and actually it's not. Just click and click on it.
Yep, there we
So
go.
it's actually look, there's an older methodology for debugging. So it's kind of like science, and it's reminiscent to the scientific method actually. And this is something that everyone can learn, and it's very, very beneficial in our line of work to learn how to debug properly. So this is why I'm giving this talk. And if you walk out of this talk, even with this, only this, that you can learn how to debug, then, I've done an amazing job and I'll be very happy with myself. But of course, there's also the methodology. And also we've previously, we've conducted a workshop for teaching people how to debug in SREcon several years ago. And the material is still available online in GitHub. I'll put the link later on. And just feel free to use that material, and there's also some books and stuff that you can use. And, it's really helpful. It really helped me, and of course, might help you. So click on it. So a few words about CLDB. I work as a developer advocate for CLDB. It's a company that creates the open source database, distributed high performance database, Scylla. And Scylla is a drop-in replacement for Apache Cassandra and DynamoDB, and it's like API compatible, so you can use the same drivers, same programs, just works transparently, but it gives you 10 times the performance and very, very, very low latency, even in the high percentiles like P99. So it's an open source that's been out there for quite a bit of time. It's been used, it's in production use by a lot of prominent companies. You can see some of the logos. And it was originally created by the same people who created the KVM hypervisor. It's a very, very interesting technology. I don't have time to talk about it, but just look online for more material or ask me later, and I'll be very happy to talk about that. Click. Yeah, so actually, don't really care about that. It's, just for marketing and promotion. Let's talk about debugging. Okay, so we're going to begin by talking about what you shouldn't do, and some patterns in debugging that happen a lot, especially when people just debug without methodology. So randomly rebooting stuff until it works is the way that a lot of people try to solve problems. And it's understandable because this is what you do when you don't know what to do, or when you don't have time, or when the system is too complicated. You just reboot stuff, and sometimes it fixes the problem, but sometimes it makes the problem even worse. So click. So the things to avoid, okay? First of all, randomly rebooting stuff. Why? First problem with this is that it basically destroys data. Okay, you have the system in a certain state, and if you reboot stuff, then you create a lot of noise, and that makes debugging a lot harder. And you can actually also aggravate the problem, which is something that you don't want to do. Second problem is randomly looking at metrics. We'll talk a little bit about that in a bit. And of course, blindly believing the monitor and metrics, because there's also the possibility that the thing that's broken is the monitor itself, or the metrics, whatever is producing the metrics, maybe producing the wrong metrics, or some artifact in the metrics, that kind of stuff. There's also the problem of human biases. For example, giving the loudest screamer all the attention. So maybe you have some alerts firing, and they create a lot of noise, and you start debugging those alerts, but they could be irrelevant or the consequence of something else that's happening in the system. And it's very easy to have all your attention going that way, although it's probably just a distraction. And of course, another bias, which is giving the latest data all the attention, or emphasize the importance of latest data, just because it's it's fresh. But that doesn't mean that it's more important or has more information value. Okay, but all of those are common patterns that we see with people debugging. Click. Thank you. So this also connects to another common bias or belief, which is that correlation equals causation. And of course, that's not true. We all know this graph on the side that shows the amazing correlation between Internet Explorer and murder rates in the US. That might actually have some causation. I don't know, probably not. But as we all know, correlation is not causation. Okay, so just because we see something that looks like it correlates from a time perspective or a timeline perspective, that doesn't mean that those things are necessarily connected, or that this is the cause of the problem. And you should remember that some problems just go away on their own. If you just don't touch the system, you leave it, some problems solve themselves. And of course, this also goes the other way, where some underlying causes vanish after a while, but the problem persists. So you might be able to fix the problem after a while, and then you look for the cause, but you can't find the cause because the cause has gone away several hours ago, but that doesn't mean that it's not the cause. So even if you look at metrics and you're looking for some correlation, you're not necessarily going to find it, even if those things are related. And this is even much more of a problem where you have several people tending to the system at the same time. And this is something that happens a lot during major incidents, where basically it's all hands on deck, and you have a lot of people working on the system simultaneously and creating noise for each other, and it's very hard to understand what relates to what. Click. So to give you kind of an example of the biases and how they work, we're going to talk a little bit, we're going to do some kind of a mental exercise. So the situation that I'm going to talk about is that we have a breathalyzer. The police have breathalyzers to check for alcohol for people who drunk drive. So the breathalyzer in this case detects all drunk drivers, meaning that it has no false negatives, but it does have 5% false positives. And then the police stops drivers at random, and they pulled over a driver, and they checked him with a breathalyzer, and the breathalyzer shows that the driver is drunk. So the question is, what is the probability that the driver is really drunk? So I'm going to give you like 20 seconds to think about it, and then just click.
I want people to shout out in the chat, Abishai.
Yeah, okay, so we've got some answers, 5%, plus, click, that's the answer. So if you answered something like 25%, 95%, so you're wrong, and you've fallen for the base rate fallacy, okay? This is a very common misconception. The correct answer is about 2%, which is astoundingly low, Okay, click on it and you see the explanation as to why. And the explanation is, and this is why it's called the base rate fallacy, is that actually drunk driving is very, very rare. Okay, if we have a random sample of 1,000 drivers, let's say that we check like millions of drivers, we would find that one of every 1,000 drivers is actually drunk, but we will have about 50 false positives. Remember, we have 5% false positives, so 50 people out of every 1,000 drivers would be falsely detected as drunk. Okay, so the base rate of false positives is much higher than the rate of drunk people, of drunk drivers. So we have a 50-to-1 ratio of false positives to, to true positives. Okay, so this is why it's 2%. And this actually confuses a lot of people, because you don't, when you're dealing with detection, you're usually thinking only of the thing that you want to detect and not of all the noise and the wrong answers that you might get. Okay, so this is a very big problem in medicine, in law enforcement, and also in monitoring. So click on it. So if you're looking randomly at metrics and you're looking for errors, it's pretty much guaranteed you're going to find errors. They're going to be irrelevant errors, okay, but you're going to find errors. Why? Because the base rate of errors in our systems is very high. There's always errors. We just don't see them because we don't look. And if you look at the system that's working properly, you're still going to find errors. So that's a big problem. Click. So errors are kind of a normal situation in system, and any big system will have a lot of statistical errors. If you look at graphs and you have like a reasonable throughput, even you're going to have always like 0.01% of errors, sometimes more. You're going to have lots of different types of errors as well. You're going to have various anomalies, timeouts, weird behavior from users, whatever. And if you just search for errors randomly, you're going to find them for sure. And they will not be related to the problem that you have. So the thing to remember is that the base rate of error is relatively high because we don't have a lot of incidents. The whole point of having a reliable system is that we don't have a lot of incidents. So almost by definition, we have this problem of the base rate fallacy. Click. So the lesson here is that without constructing some kind of a theory, basically there's nothing we can do with data. Okay, the data is just going to mislead us. We're going to look at the data, we're going to find some patterns that look interesting or look suspicious or whatever, and we're going to follow those patterns despite those patterns having no connection to what we're debugging. So we need to construct a theory and connect what we see in the data to the theory, and actually even more importantly, we need to use the theory to construct the questions before we look at the data. Okay, click. So now this brings me to talk about the actual methodology of how to do this. Click. So the methodology is constructed of 7 parts, and of course this is computer, so we're going to start from 0. It's 0-based array. So first, triage. We're going to talk about each step separately in a bit. So triage, define and narrow down the symptoms, build a method model of the system, deconstruct, create and revise a theory, corroborate the theory, and then reconstruct and validate, and of course rinse and repeat until you're done. Okay, click. So first, phase 0, triage. Okay, so what is triage? Triage is like you do in ER. Okay, you don't have enough capacity to handle all the problems, so you need to focus and only handle what needs to be handled urgently. So what we do in the triage phase, it's a very quick phase. It usually takes a couple of minutes, and it's very helpful to train to do this. It's not very hard to train to do this. You can just do this over lunch, construct some kind of mock scenario and just discuss it with your colleague. And what we're trying to answer in this triage phase is stuff like, what is the business impact? Is this actually a business problem that we want to take care of? Should we handle this at all? Maybe not. Some problems, they don't have a lot of impact, so we don't do anything about them. Maybe the problem will also go away. We sometimes, even in the triage phase, we realize that, okay, we have an outage because we have too much traffic, but this is due to an event that's going to be over in 20 minutes. By the time we add capacity, the thing is going to be over, so no point doing anything. Should we handle this now? Okay, can we delay this to Monday, maybe, or maybe put in some mitigation and then deal with this during business hours. So all those decisions can be made during the triage phase, and it's worth training for this, because this needs to be done very quickly. Because remember, every minute that we're spending on triage is a minute that we're not spending on actual debugging. Click. So once we decided that we want to handle this, then comes defining and narrowing down the symptoms. So the problem, one of the biggest problems when you get an alert or someone reports a problem, is that the description is very vague, and it's very hard to work with this. Very hard to recreate issues when you have a vague description of the problem. Very hard to isolate, the conditions in which a problem occurs. And this brings me to talk about something called operational definition. So what we want to get, we want to distill an operational definition of the symptoms of the problem. So what is an operational definition? It's a combination of a method of checking something and the expected results. Okay, and we're trying to answer the questions, when is this happening? Where is this happening? To whom? What users and which conditions? So I've got a couple of examples, but just to give you an idea of what this is, you execute an HTTP GET. This is the method of checking, and the expected results are that you should get 500 status response from the HTTP GET. And this only happens from the US, and it happens with every cookie that you send in the headers and so on. Okay, so this is what an operational definition should look like. Click. So a couple of examples. Okay, so I gave an example of HTTP, but note that in this example, for example, I said that this only happens in 5% of cases. Most cases, when we have a problem, it's usually a partial outage and not complete outage. So having something like this happens in 5% of cases is very important to say, because if you omit this, then the person that you're talking to is going to run CORL, and it's going to get 200, and it's going to be like, okay, there's no problem. But if you would have run it, let's say 1,000 times, then he would have detected the problem. So it's very important to emphasize things like, what's the probability of this happening, okay? Especially if you're debugging something like elevated error rate. Latency, okay? So here, the operational definition includes an aggregate, in this case, P99. So the P99 of a transaction X is over 500 milliseconds, and look how the operation definition says over, okay? So for all time intervals since 1 hour ago, and it should be under 100 milliseconds, okay? So what is the result that we're getting, and what do we expect to get? Transaction Y should return for user blah, blah, blah. This is a problem for a specific user. It returns empty records, but it should return 100 records. Okay, so those are examples of good operational definitions. And again, worth training for this. It's not very hard to do, just something that you need to get used to. And it saves a lot of time and a lot of misunderstandings when we debug things. Click. So once we have an operational definition, this is when we actually go into debugging. Okay, now we can start debugging. So the problem is that we all have a mental model of how systems work, okay, in our heads. And we have those kind of models for anything that we interact with, and they include a lot of implicit assumptions about how stuff works. And the problem is that most of the time, our mental model is wrong, okay? And also it's never ever complete, because the universe is infinitely complicated and we can only fit so much stuff in our heads. So the mental model, even if it's not outright wrong, it's definitely not complete. And the problem is that we need to make this model explicit, because otherwise we cannot debug and fix it and improve it. Okay, click. So just an example. Okay, how does a microwave oven works? Okay, so the microwave oven has a power knob and a timer knob, and then you ask people, how this microwave works. What happens when you change the power knob? And people say like, oh, okay, so it just heats up less. So they assume that the microwave has a heating body, or radiation, and the amplitude or the strength of the radiation is controlled by the power knob. So this is the mental model of how a microwave operates, and it's completely wrong. Okay, so the way microwave operates, and also by the way, air conditioning also operates this way, is that when you change the power knob and maybe you put it in like 50%, what happens is that the thermostat inside the microwave or the AC turns on and off the power heating element very quickly. Okay, because it can only heat up in one fixed temperature. Okay, it doesn't actually adjust the temperature, just adjusts the percentage of time in which it's on. Okay, and it's the same for air conditioning. The air conditioning unit also cannot change its temperature. It can only switch on and off very quickly. Okay, so and in AC actually it switches on and off very slowly even. So this is an example of a mental model that seems obvious, but actually it's not obvious and it's completely wrong. And it's not a problem until stuff breaks and doesn't work as planned, and then we have to make those assumptions explicit and understand where the mental model deviates from reality. I'll click. So another example, counter steering. If you ride a motorcycle, you already know this, but if not, then if you look at the picture, you see that although the guy is leaning to the left and is taking a left turn, the wheel itself the front wheel is turned to the right. Okay, so this is called counter steering, and it's very counterintuitive for people who see this for the first time. Because as someone who's new to motorcycles, you assume that to turn left, you're gonna, you're gonna steer left with the handle, and actually you should do the reverse. You should steer to the right. And I was riding motorcycles for a very long time, and I was actually very surprised to hear about this because I was doing this without even noticing. And then I started looking at my hands, and I saw that yes, indeed, I was actually turning my hands to the right when I was turning left. So very confusing and very counterintuitive, but this is how it works. And this is another example of where our mental model is completely wrong and deviates from reality. Click. So what do we do? Okay. First of all, we need to make the model explicit. Usually we do this by drawing a diagram and listing our assumptions on the diagram. And then we confront this with what we know. And sometimes things just don't make sense. And then we have three options. One option is say, okay, we don't have enough data. Something is missing here, so let's get more data. Option two is the data that we have is wrong. This is always an option, and this is something worth remembering. It could be that the model is correct, and we just got data that is bad. Okay, so sometimes thinking about the possibility of the data is wrong is very important, and you can always get data again or check what can possibly be wrong in the data. And then there's a third option, which is the most common one, which is the mental model that we have is wrong and we need to change it. We need to tweak it. Okay, click. So how do we do this? What we do is we deconstruct the model, and then we create and revise a theory. Okay, so we take the diagram that we have, and we disassemble the system to subsystems. And we, on the diagram, put the connections between the systems. And this is important because sometimes we see that, okay, maybe we forgot a connection between two subsystems. So we look at the diagram and we see two subsystems and there's no connection between them on the diagram, but we know that there should be one. Okay, so, okay, we're missing something. Let's check, what's going on. What is the input and output of each subsystem? Data goes in, something goes out, and so on. And then we can start to speculate and create a theory about which subsystem or a connection between the subsystems is, a potential cause of the problem or related to the problem. So we construct it and we create a theory, and then click. After we have a theory, we can corroborate the theory. Okay, so how do we corroborate the theory? First of all, we define what metrics or experiments we need to do to get to validate or prove or disprove the theory. Okay, so this is very important. First of all, because there's a difference between metrics and experiment, and the difference is that metrics is something that you already have, whereas experiments is something that you do to the system to get more data. Okay, so experiments is usually something that is done actively, and it might have side effects. So you need to design for it, okay? And you need to sometimes do it in a controlled fashion, especially if it's during an outage, because it could be something like, let's reboot one of the servers to see, what messages we get during boot. Okay, that's a kind of an experiment. Or let's apply this load to this server, this specific transaction load with those characteristics. And this is a type of experiment, but it might be dangerous, okay? It might aggravate the problem. It might have some side effects and so on, so on, so on. So experiments is something that we do a lot, but this is also something that we need to design for, okay? Metrics is much easier because you already have it, probably. So usually the first priority will always be metrics and experiment second, but often we don't have enough data, so we are forced to do experiments. So you define what metrics and experiments you need to do to corroborate the theory, and then you define the expected results from those metrics and experiments, and only then do you get the data. Okay, click. Why? Confirmation bias. Okay, so confirmation bias is one of those things that are very, very basic to humans, and also one of those things that are most dangerous when you're debugging systems. So we all have a tendency to reject the data that doesn't agree with what we think already, and only accept the data that confirms what we believe. Click. And because of this, okay, the way to avoid confirmation bias and avoid confirming our pre-existing beliefs or hypothesis is that we need to decide upfront, before we look at the data, before we do the experiments, we need to define exactly what we're going to check and what the results that we expect. And I actually write it on paper. This is what I expect to see, because otherwise it's very easy to lie to yourself and just tweak the what you thought you're going to see in retrospect, and they're like, oh yeah, of course, this is what I thought. No, actually it wasn't. I just lied to myself. And apparently humans are very good at doing this. So kind of disturbing and also potentially very problematic when you're debugging. Click. So once we did this and we have data, we collected data and we corroborated or we did not corroborate the theory, we do another very important step, which is reconstruct and validate. Okay, so remember in step 3, we deconstructed the system into subsystems. And the problem with this is that sometimes what is happening is the interaction with the subsystems that is doing this weird phenomenon that you're seeing. So you deconstructed the system, you find something in a subsystem, and actually that something is unrelated. So how do we find out? We reconstruct the system, and then we see in the reconstruction if the reconstruction still holds. Okay, so what do I mean by this? So first of all, we have something called system invariants. Okay, things that should always be true about the system. For example, Litter's law, which is kind of a mathematical law for queuing. This as the client to the system should equal latency times throughput. Look it up in Wikipedia later. And this is something that's universal and should always hold. So if we compute Litter's law for the metrics we have, and we found that it doesn't hold, this means that something is very, very wrong. Okay, all the data that goes in should, all the transactions that goes in should equal the amount of transactions answered plus the amount of errors. Also system invariant. If not, something is very weird. So we check those system invariants, and this is how we make sure that we didn't miss anything. Okay, and we compare the data that we got to expected results. And we check the interconnections between the subsystems. So this is why it's called reconstruction. We reconnect all the subsystems. And we see if what we found in the theory, it still validates what we expect and holds. And if not, then we go back to the drawing table, we say, and we check it again. Okay, probably we missed something. Okay, this is something very important. When you draw a diagram, you're only drawing the parts that exist. Sometimes there are parts that don't exist, and they could or don't exist on the diagram, okay? And the only way to know that you're missing something for the diagram, in other words, to know what you don't know, okay, is to do this reconstruction phase. And then the reconstruction phase, you're like, okay, the problems that I found do not explain the symptoms that the system as a whole has. Okay, so this is why this phase is crucial for debugging. Click. So once we did this, then we get to the rinse and repeat phase, which is, did we find the cause of symptoms that we're dealing with? If we did, great. Now we can devise a plan to deal with it and fix this. If we didn't, there's two possibilities. One, we narrowed down the problem to a subsystem and it's contained in the subsystem. Let's say that we found out that the database is broken. So now we can restart the whole process and just debug the database itself and forget about the rest of the system. This is actually a very good result because it means that now debugging is much easier. And there's another possibility, which is we didn't find the problem and then we need to say, okay, the theory that we devised is wrong. The model is wrong, or it's lacking. It's not complete enough. So we need to go back to step 2 and revise the model, improve the model, get more data, and so on, so on, so on, and then rinse and repeat until we eventually find the cause or find the subsystem that is faulty. Okay. The thing to remember here that in a complex system, there is no such thing as root cause. I know that this is in our industry, root cause is something that gets thrown a lot, and you have fancy root cause analysis systems and stuff like that. But actually, it's bogus. Root cause is kind of an illusion. It's something that we believe about systems, but in complex systems, we have a lot of interactions. So it makes more sense to talk about contributing factors. There's no single cause that on its own causes the problem. So when we debug, sometimes we might find several causes that, the interaction between them cause the symptoms. Sometimes we might find just one cause, but in a sense, it's a belief. Because yes, this is maybe the latest thing that happened or the most major one, but it's definitely not the only one. And even having defenses that broke down, that is also in a sense a contributing factor. So this is something that's very important to remember when you debug. Lindsay, how much time have we got?
I'll be honest, I haven't been keeping track. How much longer do you want to go for, Avishai?
So click on it for a second. So there's another part which is how to look at metrics and stuff like this, which you can go through. It takes about 5 to 10 minutes. So if you've got time, I would like to go through it. Yeah, just keep it to 5. That'd be great. Just we want to finish at a reasonable time here. Okay, so go for it or not? Okay, cool. So how to look at data? Okay, so first of all, is what are we looking for? Okay, so the question is, when we look at metrics, what are we looking for? We're looking for outliers, we're looking for high values, for low values, and which aggregates should we look at? There's a lot of different aggregates. So it's very important questions, and we need to define upfront what are we looking for in the data. Click on it. Second question is, what are we looking at? Okay, so we look at the metric, and the metric says something like memcached latency. Okay, great. How was this measured? Was this measured from the driver side, the client side, or was it measured from the memcached server side? Because it's very different. One of them includes network and potentially the garbage collection of the driver, the other does not. Okay, which aggregation method was used? And every aggregation method has its own problems and reshapes or actually has different artifacts of data. Okay, so knowing which aggregation method and how was this aggregated? Was this aggregated inside of the server? Was it aggregated on the collector and so on, so on, so on? It's very important because it means that the metrics will behave differently. So knowing what we were looking at, what is this metric? How was it constructed is also very important. Click. So knowing this, we can choose the correct metric to look for and to look at. So if we're looking for outliers in the system, okay, let's say that we're looking for the clients that are misbehaving or the several servers that are misbehaving. When we're looking for outliers, we want to look at percentiles, like the high percentiles. We want to look at the max aggregation. We want to look at the topmost. Some metric systems or observability systems have this aggregation. For example, ELK has this. Most deviants which is like the topmost and the lowermost, which is basically the elements which are further away from, the most further from the average, okay? If we're looking for utilization, then we're looking for sums. We're looking for totals, averages and sums. If we're looking for errors, then we would go with error counters, of course. And if we want to compare to baseline, okay, to get a sense of how much this metric deviates from, from some baseline, then we want to compare with previous time frame, maybe last week, depending on the seasonality of the system, and of course, averages. So we can take an average of several days and then compare what we have right now to the average or the median, okay? So this is how we construct the baseline. And trends, when we look at trends, the problem with trends is that we have a lot of noise in metrics. So what we need to do to the metric before we look for trends is to apply what is known as a low pass filter, which is usually a moving average, okay, exponentially weighted moving average or whatever you have in the system. And this basically removes the noise and then you can see the trend. There's also a technique for trend detection, which involves comparing two moving averages. I'm not going to go through it here. You can look for it online. Next. When we look at latency, and this is very important, first of all, we want to look at percentiles. Looking at average latency is usually meaningless because no client feels the average latency. They only feel the latency of the transactions that they executed. So to get a sense of what's going on with client experience or customer experience, we want to look at percentiles, not averages. Very important. And to understand how much resources used or utilized, we want to look at the sum of latency, which is like the latency of all transactions summed, or the percentile, the high percentiles is usually P99 because of what is known as head of line blocking. Again, look it up online. When we compute stuff like Little's law or the use method, which again, look for it online, we use averages. And when we look at bounds, system bounds, okay, so we want to look at timeouts, for example. Okay, so everything above a timeout means it's out of bounds and it's basically an error. So, and the most important thing is that every time you look at latency, you always have to look at the throughput as well and the errors and the aggregation window. This is something that many people miss. They just look at one graph. And why is this important? Because, for example, if you have a throughput of less than 100 per time window, then actually percentiles don't mean anything, because you cannot compute a percentile, let's say 99 percentile, if you have very few data points. If you have less than 100 transactions, P99 doesn't mean anything. It's just bogus. It's an artifact of metrics. So you need to see that you have throughput in order to validate that actually the percentile metric that you're looking at is actually valid and makes sense. And so, likewise with errors, okay? Maybe you see a lot of throughput, but if you also have a lot of errors, maybe you should be suspecting that something is wrong. And same from percentiles. If all the, let's say, potentially slow transactions have errors, then the percentile curve is going to be amazing, right? So again, this is why you want to check, always check all of those. It's actually a graph set, okay? You should have it on the dashboard, all those graphs together. So you never look at only the percentile graph on its own. Click. And lastly, when you're looking at errors, you always want to compare with the baseline because, okay, so there's a spike of errors. So we have 0.5% of errors. Great. Is this normal? It's quite possible that you always have this amount of errors. So you want to compare it with the baseline and, of course, compare it with the normal throughput, because 100 errors per second might or might not be meaningless depending on how much traffic you have. So basically what we're trying to understand is, is there a statistically significant difference between the errors that we see and the normal state of the system? That's basically what we're trying to ascertain. Click. Okay, and we're looking for high cardinality data, stuff like IDs, IP addresses, and domains. So the aggregation that we use for that is top K, most deviants, and of course unique counts. A lot of systems provide this as estimates because it's very expensive computationally. Hyperlog, those kind of methods, you can see them everywhere. Click, and this is, I think, the last slide for this. So there's a few established methods that I highly recommend that you go with. There's of course the 4 golden signals in the SRE book, and then there's the use method, which was popularized by Brandon Gregg from Netflix. And again, I highly recommend that you go with this. And now you can click, and we got to the questions part, which is the most amazing part of any presentation. And truly, if you don't have questions about the presentation, then you might have a few questions about this picture, which I'm not sure I have answers for.
Any questions about the presentation or the picture? Both are equally legitimate. Feel free to either unmute or you can pop them in the chat and I'll ask. Probably got time for maybe 1 to 2 questions.
There's just so much going on in that picture that I don't know where to start.
Yeah.
He's holding umbrellas, and yeah.
Maybe the question there is, where should we start with that picture, Avishai?
I would start with the guy in the back looking like an Egyptian.
Definitely. We've got a question there in the chat. Do we get a link to the deck? Yes. If you scroll back in the chat, you can see a link to it there, but I'll make sure it gets posted on the Meetup page as well, so you can have a look afterwards. If you're okay with that, Avishai, I should double check.
Yeah, sure.
Brilliant. All right, and there's one question there from Paul just asking, can you put the references in the chat? I'll leave that to you, Avishai.
Okay, I will in a second.
All right, we might call it there. Thank you very much. That was a really interesting talk.
Happy to do it.
Brilliant. All right, let me. Oh, there's a bonus round. I'm not gonna steal the thunder. Let me go back to the other slides. All right, let's get into the next little bit, which is events. So quick reminder, we've got a DevOps Days that's in the works down in Melbourne on October 28 and 29th, which is a Thursday, Friday at the end of October. So if you haven't been to a DevOps Days, definitely a worthwhile conference going along to. First half of the day is structured talks. Second half of the day is open spaces where you get to network and ask questions, and it's a very in-depth learning experience. So I highly recommend getting along to that if you can. Otherwise, there's also DevSecCon that's happening online on June 24th. So it's a really great mix there of application security and operational security content. So definitely recommend jumping along to that if you possibly can. All right. I mentioned this at the very beginning, but we're going to do a quick job section. So hopefully you've had a bit of a think about if you want to talk for a second. I see Michael has put up his hand, both figuratively and literally. So Michael, I'll give you the mic and take it away.
Hi, sorry, yes, 30 seconds, very good. Hi guys, my name is Michael, can you hear me?
Yeah, we can hear you just fine.
Very good. My name is Michael Dousman. I'm here with my colleague Michael, so we're the two Michaels. We are working at the Children's Medical Research Institute. So Genes for Genes, that's us. You can wear jeans if you wish. We're trying to fill a senior DevOps position. It's in a small team. You would make it 4. You would be the 4th member of the team. We've got some toys to play with. So we're running an on-premise HPC, 12 blades, Nimble, an Apollo cluster for storage. So some pretty interesting toys to play with. We also do a lot of work with AWS and Kubernetes, and in fact, we've got a hybrid Kubernetes cluster. I'm trying to get this right. That actually has nodes based both on our local HPC and in AWS. So that's pretty interesting. That took some time to get going. What you would be doing for us is you would be working for me, and you would be supporting a world-class data science team, and also a super cool group of lab technicians who are running proteomics research. So basically research into cancer, and a lot of interesting a lot of biology in 2021 is computation, and we really help our science colleagues get all of their computations done so that they can, write the papers and make the scientific insights and get sort of insights into different types of cancers. So it's super interesting. You'll be super interesting at parties, I 100% guarantee. So if you want to do some kick-ass IT and help cure cancer, check us out. I've got the link to the position on the Meetup page, and I'm also going to drop it into the chat.
Fantastic. Thank you, Michael. I only have one quick question, which is, what are parties? I've forgotten what those are.
They're things we used to do.
Great. You're future-proofing your social life then. Fantastic. All right. One other person to put their hand up. We've got Jesse. Take it away.
Thanks, Lindsay. Yeah, so I work at Puppet on the professional services engineering team. I'm managing the team for APAC, and we're looking for more engineers. So if you, have done some sysadmin, preferably pretty decent at it, and or programming, preferably if you've got Puppet experience, amazing. But yeah, we're looking to grow our team to help our customers implement Puppet. So yeah,
Awesome.
That's all. Thank you.
Thanks, Jesse. All right. Anybody else that is looking to talk about either themselves or a job that they're hiring for? All right. That might be it then. Fantastic. Well, if you've got any details of those jobs, Jesse and Michael, feel free to pop them in the chat and also on the Meetup page so people can follow up with both of you. Last thing for tonight, we've got the lightning talk. So we've got Michael Richardson talking about scaling SBS on demand for season 4 of The Handmaid's Tale. Michael, I will stop sharing the screen and I'll hand it to you.
No problem. Thanks, Lindsay. Can you hear me okay?
I hear you just fine.
All right, now for the next test. Can you see my screen okay? Now.
Hey, there we go.
Right. I'll even go for attempt full screen. Let's see if that even works. Is that still working?
Yeah, we can see you full screen. Amazing.
Okay, so hey everyone, my name's Michael Richardson. I've been working at SBS for the last 18 months. I was going to go with the assumption that everyone on this call knows what SBS is, but like we've seen earlier, it's an international crowd that's come along here today. So I'll give a quick overview of what SBS is. It stands for Special Broadcasting Service. So we're a broadcaster in Australia. We're largely government funded, but we also have a couple of commercial sources of revenue, mainly advertising. We've got five TV channels. We've got about 7 radio stations. We've got a whole bunch of online content. There's about 18 different websites that we support, from news to sport to cycling to all sorts of different things. We also have a video streaming service called SBS On Demand that is essentially what I'm going to be talking about here today. And so if people are curious about, if you weren't familiar with SBS, you know, sort of wondering what we're here to try and do, we're here to provide like a multilingual, multicultural radio, TV, online information to as much of the Australian population as we can do so. So that's sort of the general purpose of SBS. And now we'll get going with this talk. So I've called it People Love a Dystopian Tragedy, Scaling SBS on Demand for Handmaid's Tale. So, and just to be really clear here, the dystopian tragedy is the storyline of Handmaid's Tale. It's not about my team's efforts at trying to run an online streaming platform. So Handmaid's Tale season 4 just came out from Hulu. It's SBS bought the rights to that. We certainly had the rights to season. This is season 4. We had the rights to season 3. I think we might have had the rights to seasons 1 and 2. But like I said, I've only been with SBS for the last 18 months. But it's hugely popular. I can share a little bit of information. After the World Cup soccer, which happens every 4 years, Handmaid's Tale is the next biggest thing on the on-demand platform. So it's a big deal for SBS. Let's have a quick look at a very simplified architecture of what on-demand and the API, the SBS API looks like. So you can see here that that picture of a TV is meant to be a smart TV watching SBS On Demand. They go through Akamai, who've been having a bit of a rough afternoon here in Australia, but thankfully not impacting us. And then you go into that orange circle, which that's meant to represent an Amazon load balancer. So everything after that orange circle going down into the green boxes, the pink boxes, and the blue boxes is all stuff we run in Amazon Web Services. Most of this architecture is pretty old. most of it's being replaced. So we've got some really exciting projects going on at SBS, where a lot of this is all being replaced by new shiny things. But for the time being, for the last at least 5-6 years, this is the technology that's been running and powering the SBS on-demand systems. So it looks like a pretty traditional stack there, and we'll dive into some of the different bits and pieces in a moment. But as I mentioned, like, it is being replaced, but sort of not quickly enough. So some of the activities my team's been focusing on for the last 12 months on this is just trying to improve the automation, improve the monitoring, improve the logging. Why are we doing this? Not because like they're really important things, but more like we want to build the confidence in our tooling and our systems so that we can rapidly make changes in a really safe way. So when the business comes to us and says, hey, team, in 2 weeks' time, season 4 of Handmaid's Tale is going to launch. Can we be ready for it? We want to be able to confidently say, yes, we can. So that was a conversation we had totally about 2 months ago, preparing for Handmaid's Tale. Lots of good stories within SBS, good collaboration between the business, the on-demand team, the team that sort of manages a lot of the things in AWS. Bit of a background story. So they did have a few issues with the previous season that was on 2 years ago. Like I said, I wasn't here for it. Not that I'm saying I would have helped at the time necessarily to alleviate any of these issues, but it was a massive surprise to a lot of people. The uptake that the show had, and some of the issues that the team there at that time had with trying to make sure that the API and everything was still working. And we just all wanted to make sure that it would just be a lot more smooth sailing this time. So let's look at some of the challenges that we've got. The database you see down in the bottom right-hand corner, it says Amazon RDS. We actually use the RDS Aurora product from Amazon, which is pretty cool. It does like it offers resiliency because it's across different availability zones. It does like auto scaling by adding what they call read replicas, so that above a certain load, it'll just add more read replicas. It does automatic failover, so it's good at availability. That all sounds really nice and really important stuff. It actually doesn't suit us too well. So our relational database here is actually very write heavy. And the way we use Aurora, we actually have to scale vertically. We can't really scale horizontally to deal with increased loads. So one of the challenges we had here is we had to essentially look at all of our analytics and monitoring of our current systems, factored it in with the expected growth or patterns that on-demand team was expecting for Handmaid's Tale, and we just had to scale vertically for it. So not ideal, and actually we'll dive into it in a little bit more detail towards the end of the lightning talk. It's not a very good choice of technology for what it actually does on the on-demand platform. But like I said, it's all going to be replaced shortly, so can't wait for that to happen. Next slide, Elasticsearch. So that's the database that's on the left-hand side that looks like a whole bunch of blobs of color stuck together. That's the Elasticsearch cluster. Some of the problems that we sort of have with that is like it doesn't offer any really clever, amazing auto scale up, auto scale down type features. You just sort of set it to be, well, this many nodes, please, with of this type, this big, and there you go. You can sort of change the cluster size, but it takes quite a bit of time. So it's not the type of thing that you want to do multiple times per day at all. And so I sort of look at this cluster and I sort of think that it wastes quite a bit of money when it's underutilized, and it just gets really slow when it's busy. So maybe there's things that we could do within the application, or we could be using that other data. Well, I don't know if Memcache is really a database, but that other box in the middle of those two, whether we could be accelerating things, but it's just not easy to deal with auto scaling of Elasticsearch. Let's go to the third challenge, which is our traffic patterns. I'd describe it as predictable, but spiky. So for those databases, we sort of have to set a particular size and just sort of go, that's good enough to deal with our expected peak volumes. For those API servers you see in the middle of our technology stack there, we run those on Amazon EC2, so on virtual machines. We use auto scale groups that scale up and down based on demand. So, you know, at 4 o'clock in the morning, we're running 4 of those servers. In 2 hours' time, we're going to be running about 60 of those servers. So that's really cool. We scale up and down. We're using what we need. The challenge we have, though, is you'll see some of those spikes there. That particular graph is shown over like a 3-hour period, our peak period. Some of those spikes you see there are really hard to just automatically deal with auto scaling. So we have these auto scale policies that sort of say, well, if the load on our nodes is above a certain threshold for a certain period of time, then throw some capacity into that group. It's often not quick enough. it just won't come up high enough. So we've tried a couple of different strategies to deal with this. We previously used to scale up the size of our clusters if our CPU load was above 60% for a consistent 2-minute period. And then we thought, well, maybe we should just drop that down to 50%. So if we hit the threshold of 50% on our nodes, then we should scale up then, basically giving us more headroom to allow us to accommodate spikes in traffic. That isn't quite enough for us. We still can't scale up quickly enough. So we've actually introduced a couple of techniques where we've, because it's quite predictable, these patterns, maybe the color's not too easy to read, but the very first spike you see there is at 7:30 p.m. So we've got some analytics that sort of tells us there's a lot of people who watch, SBS broadcast TV, and at 7:30 they flick straight over to SBS on demand. So we get this massive spike in API activity that occurs right then. So in AWS, we had CloudWatch scheduled events that run some Lambda that go and determine what is the current size of the auto scale group and just go and increase it by 20 nodes. Sort of a little bit blunt as a way of dealing with it, but it gets us through any of these particular spikes that we see. Now, this next slide is us just sort of, I'm overlaying the size of the auto scale group over like a 3-day period. You'll sort of see it goes up, often with this blunt instrument of throwing a bunch of servers at it. Often we throw too many at it, but it's hard to know what's too many 10 minutes before you're expecting a spike in activity. So that's a little bit of a downside. We often increase the size of the auto scale group, and then it realizes that was probably a little bit too much, and then it scales it back down slowly. Let's go next. You'll see the SBS web servers represented in green there. The challenges we have with that is we run Nginx and we have no challenges, actually. Nginx just works. It is so fast at what it does there, which is not much, to be honest, but it's every single request that comes into our environment goes through Nginx, and it sends API traffic to the API servers. It sends our CMS traffic off to Drupal. It sends traffic to all sorts of different places, but it is so fast. A former colleague here at SBS was just so impressed with SBS that he decided that if he was ever to have kids one day, he was going to name his child Nginx because he was just so impressed with it. It's so fast. I kid you not. We often run only about 4 servers there, and I shouldn't divulge too much, but they're T3 micros. And of an evening, they'll do 1,000 requests per second, and they're breaking a bit of a sweat at about 10% CPU usage. So they are just flying. So challenges, Nginx, no, not really. It just works. So anyway, we've done all this prep. We've sort of adjusted our scaling policies. We've scaled certain things up. We've added some more rules to our auto scale group. We're thinking we're ready to go for season 4 of Handmaid's Tale. But a week beforehand, we always just wanted to think through, what do we do if things go bad? So what happened if the forecasting numbers were wrong? What happens if we've started to encounter limits to our systems that we've just not seen before or weren't expecting to experience? Do we have any thoughts on what we want to do about this? And when you design systems like this, rather than have the entire system crap itself as soon as it sort of gets under load or as soon as the slightest thing starts to fail, what you're looking for is, can we try and degrade gracefully in our system? We're looking for opportunities to disable essentially non-essential, non-critical features while keeping the overall service working for our users. So we had a bit of a think about this, and the obvious to us that sort of manage this system day in, day out, and the on-demand team themselves, is to look at the video progress update. So video progress update features are common across all the streaming providers. That's where you sit down in front of SBS On Demand, iView, Netflix, you're watching something, you hit pause, you come back tomorrow, and it says, do you want to resume where you're up to? Or maybe you switch from one device to another device, you were watching it on your smart TV, now you're watching it on your iPad, and do you want to just continue where you're up to? So video progress, really common feature, users love it. It is so, the way SBS implements it is that your device, like your smart TV, sends an update through our entire stack every 90 seconds saying, oh, hey, this is Michael here. I'm watching episode 2 of season 4 of Handmaid's Tale, and I'm 90 seconds in. I'm now 180 seconds in. I'm 270 seconds in. Sort of doesn't sound like much, but of an evening, our API servers are getting well over 1,000 video progress updates every single second. And our data store of choice, which I sort of alluded to earlier, is not really ideal, is a relational database. There's all sorts of different technologies that would probably be a better choice than that these days. But this is the thing that will just absolutely smash our systems. So then back to the, can we look at degrading gracefully? Nginx, that thing that we just all marvel at, that is so fast at doing everything. What we'd like to do is, can we find a way of disabling video progress? We don't have a special way of informing all the devices out there to no longer send their video progress updates, but instead, Nginx sees all the requests coming through. And so we had a trick up our sleeve, let's call it, that if we thought that systems were starting to fail, if we thought the on-demand platform was going to fall over due to excessive load that our systems couldn't deal with, we had a change ready to go on our Nginx servers if we needed it, which would effectively grab any of the video progress API updates at Nginx and just automatically respond with a 200 OK back to the client device saying, yep, cool, we totally saved that, even though we didn't. Now, this particular like I said, trick up our sleeve, we haven't had to use yet. So that's really good. But I think it's sort of always handy to think about these things. How might you want to deal with problems that might come up that you're not expecting? One also thing just to allude there, like I said, we often run maybe about 4 Nginx servers. So we could have totally just blocked it on all 4 servers, resumed the on-demand service, and then decided that, well, maybe we'll let the video progress update traffic go through on one of the 4 servers. So instead of completely breaking the video progress update feature for all of our users, we'll just make it slightly degraded so that instead of your video progress being saved every 90 seconds, it might be every 5 minutes instead. So Nginx there, super powerful for us, even though it's a bit of a dumb web server that just is acting as a reverse proxy. We could start to do clever things like that, like sort of protect a lot of our systems by rolling out small little changes like that. I think that's the end of the lightning talk. Just wanted to shout out here, I didn't mention it earlier, but SBS are hiring at the moment. So the first 2 positions there are actually on the on-demand video streaming team. We're after back-end developers, people who are familiar with cloud, infrastructure as code, and most of those services are being written in Golang. We've also got a couple of other, we've got another project going on within SBS, which is a CMS project. We're after people with more Java skills on that particular team. So if any of those particular roles are of interest, that's my email address there, and I've got a Twitter handle there. Either of those things, if you want to reach out with any questions about either the talk or the jobs, by all means, do so. I'm happy to take any questions if there are any.
Great, thanks, Michael. There's actually 2 questions that popped up in the chat while you were talking, so I'm just going to repeat them here. The first one was, for the Elasticsearch that you're using, is that using the AWS managed Elasticsearch?
It is, yes.
Fantastic. And the second question here is, I'm going to quote here, on the up and down nature of the incoming writes, how much of that is queuable? Yeah, it could be. Yeah. So potentially, instead of doing an update on every single individual video progress update, we could batch update them. Yeah, could be. When I said earlier, like, this whole thing is being replaced. So we were trying to decide how much optimization do you want to do for a platform that you're hoping to completely decommission and replace over the coming months. So yeah, batch updating would probably work. If we wanted to continue storing video progress in a relational database, that might make it go a bit quicker, or certainly reduce some of the load. Yeah. But I'm curious, given that you're decommissioning the current infrastructure and architecture, how do you handle that problem in a new one?
I know bits and pieces of how the on-demand product team are going about it, but I'm not completely across all of it just yet. So they're just going to be using different technologies, some of them that are a bit more asynchronous with how they write their data, and probably looking at, I think what they're looking at is probably either DynamoDB or Redis with Elastic Cache for those specific data stores.
Cool. That's good
Hey guys,
background.
I was the guy that asked that question. I was going to say that, yeah, we ran into that problem a few years ago at a company I was working at, and we tried Redis in front of the RDS instance, and that didn't work very well. So then we re-architected to Dynamo. So your answer was perfect.
Yeah. Cool. Any other questions at all? Now I've got to figure out how to stop sharing my screen. There we are.
All right, final questions for Michael before we wrap this up. All right, we might call it there. Thank you, Michael.
No problem.
All right, well, we are actually at the end of the meetup. Thank you all very much for coming. Lovely having such a great range of guests coming and speaking tonight. Looking forward to seeing you all again in July. If you've been inspired by any of the talks that you've seen here tonight, feel free to let me know and to volunteer to give a talk at an upcoming meetup. We are always looking for speakers. Otherwise, stay safe and see you online in July.